Okay, hi guys. This was from class on April 1st. We were talking about rational functions, and we investigated this function, f of x equals 1 over x squared plus 1. So we talked about vertical asymptotes. Vertical asymptotes, we look at the denominator and we see if the denominator will ever equal 0. So basically you set the denominator equal to 0, x squared plus 1 equals 0, in order to find out where the vertical asymptote occurs. And we found out that x squared would equal -1, and we're not going to square root a negative. So the denominator can never equal 0 in this example. So we have no vertical asymptote. Then we talked about horizontal asymptotes. So we concluded that if there's a higher degree in the denominator, so this is a degree 2 in the denominator, then we're going to have an asymptote at y equals 0. And one way to look at horizontal asymptotes is to picture x being really big or really small and see what happens on the outskirts of the graph there. So if x was really big, like a billion, and then you have a billion squared plus 1, you're going to have a really big number in the denominator. And when you take 1 and you divide it by a really big number, you approach 0. But you know what? The function is actually never going to have a value that's equal to 0. There's no value of x that you could input that would create, that would make the fraction equal to 0. So therefore, we have a horizontal asymptote at y equals 0. Okay, so then our next step for sketching this curve is to find the derivative and see if there's any local max or mins. Okay, so we took the first derivative. I used chain rule. So I took my denominator, x squared plus 1, and I put it to the power of -1, and then I did chain rule. So I moved the -1 out front, x squared plus 1, I subtracted 1 from the exponent, and then multiplied it by the derivative of the inside, which is 2x. And then I just rewrote it with the negative exponent in the denominator. So that was my first derivative. Some people in the class used quotient rule, and they got the same answer. Okay, then we set our first derivative equal to 0 and solved it. We concluded that we only care about the numerator. So in order for this function to equal 0, you would just need the numerator to equal 0, and that occurs when x equals 0. And then we found the y value when x equals 0 was 1. So now we know that there's a local max or a minimum when x equals 0 and y equals 1. So then we set up our intervals of increase and decrease. So we put x equals 0 in the middle, and then we checked out what's happening to the left and the right of that. So to the left, when we subbed a value into the derivative for x that was less than 0, like if we subbed a value in for x, like -10, we found out that this function is going to equal a number bigger than 0. It's going to be positive. So we know that our slope is going to be positive, so our function is going to look like this. And then when we sub 0 in, we know we are going to get a max or a min. And then when we sub a number that's greater than 0, we know that our first derivative is going to be a value less than 0. So after figuring that all out, we determined that at x equals 0, we will have a maximum, because our graph's going to go like this somehow. Okay, then we moved on to the second derivative, and I actually made a mistake here. This is why I'm making this video. Okay, so we found the second derivative 2 different ways. So you can use product rule and go through it. And actually, that's correct. I got the right answer. Phew. But when I used quotient rule, I made a mistake. See how I have an x squared here? I actually just ignored that over here. So I had x times x, and I just forgot the squared. So if you're following along with me, I totally forgot my squared there, which is definitely going to make a difference, I'm thinking. Yeah, because this would be 4x squared. That would be squared. Yeah, it's going to make a big difference. So let's just recap here. So I'm finding the second derivative. And I made a mistake. So anyways, this was my answer for the second derivative. So now we're setting the second derivative equal to 0 to find out if we have any points of inflection. And we're going to check the concavity of the function. Okay, so then I decided in order to solve this expression to make it equal 0, I couldn't it doesn't look good in that form. So I put it in factored form. So I noticed that both of these terms have x squared plus 1s in them. So I factored out an x squared plus 1, and then I also know that 2 and 8 are both divisible by 2, so I also factored out a 2. So then I went through each term and I said, okay, from this term, what do I have left once I factor out a 2x squared plus 1? So it turns out I'll have a negative x squared plus 1. And then what do I have left from the second term? That's going to change now. So I'll have a 4x squared. I forgot the squared. Okay, and then I'm just simplifying it from this part. So I have 2, so yeah, so this is going to change. Let's just redo that. Okay, so to simplify, so I set each bracket equal to 0, and we concluded that this will never equal 0. So there's no value that exists that will make the expression equal 0, the equation equal 0. So then I'll try this side. So actually, this might be easier. I don't even need to use the quadratic. I don't even need that. So negative x squared minus 1 plus 4x squared. So I can simplify that to 3x squared minus 1. Right, because 4 take away 1. And then I'm setting that equal to 0. So actually, this is a lot easier. So 3x squared equals 1. I'm going to divide both sides by 3. And then I'm going to take the square root. So x equals plus or minus the square root of 1 over 3. So I'm sorry about that. So in class, I actually just forgot this squared here on the 8x, which I should have noticed because it was here. Anyways. Okay, so now that we have the x values, we want to see if that is where the points of inflection occur. And in order for them to occur, the concavity has to change. So I'm going to say, okay, if x equals negative 1 over 3, and if x equals positive root 1 over 3. And then let's investigate what's happening when x is less than negative root 1 over 3. What happens when x is right in between negative root 1 over 3 and positive root 1 over 3? And then what happens when x is greater than root 1 over 3? And you're just going to check the second derivative, and you're going to just test the values, and you're going to see, is it going to be positive or negative? So you're just going to test that out. So here, I'm thinking we're going to be greater than 0. So you would go to your second derivative, this guy right here, and you would just be subbing in values that are less. You could sub in like negative 20 for x, and you're just going to see what happens. So you're going to see if it's positive or negative. So it looks like when we sub in a negative to x, it's all of the x's are squared. So they're always going to turn positive. And then, yeah. So I think that whole thing is going to be positive. So we know if x is greater than 0, then that shows that our graph will be concave up. I wasn't expecting that. So then we're going to see if this is a point of inflection. Okay, so what happens when x is in between the two? So let's say I set x equal to 0. Okay, I think my function is going to be negative. So my second derivative is actually going to be less than 0 when x is 0. So that means my graph will be concave down. Okay, so we are changing concavity. So therefore we know that this will be a point of inflection. And then we got to check when x is greater than root 1 over 3. You know what? Our second derivative is going to be greater than 0. So if you sub in a value up here, like 1 or something, and check what it equals, it's going to be positive. So therefore, it's concave up again. So that means this is a point of inflection too. So my original sketch might not have been that good. So if we're going to sketch out this rational function, we know there's a horizontal asymptote at y equals 0. We know that there's, I'm going to just extend my scale, but we know there's a max when x equals, or when y equals 1 and x equals 0. There's a maximum. And we know that the graph is concave up here. And then it switches to concave down and then back to concave up. So there is a point of inflection at negative root 1 over 3 and positive root 1 over 3. There's going to be points of inflection. So that's what our graph would look like. Can't seem to shut my video off.